Hello again. This is Math 2232 coming to you from the College of DuPage, and the title of this lecture is Work. And work, in this case, is a physics and engineering concept. As always, please be an active learner as you watch these videos. We begin with a simple case of what is the work done by a constant force. Now, the concept of work is important for scientists and engineers for determining the energy needed to perform various jobs. So, for example, you may want to know the amount of work done when a crane lifts a steel girder, when a spring is compressed, when a rocket is propelled into the air, or when a truck pulls a load along a highway. Now, this is the definition of work, but this definition of work is under very special circumstances. The force applied to the object is constant, and it is in the direction of the distance of the motion. So the definition of work done by a constant force then is an object is moved a distance d in the direction of an applied constant force, capital F. Then the work done, W, done by the force, is defined to be W is equal to FD, F times D. Now there are many types of forces, electrical forces, gravitational forces, and forces of rotational motion, and so those are a few. There are many, and you study these in your engineering courses. A force can be thought of as a push or pull, and a force changes the state of rest or the state of motion of a body. For gravitational forces on Earth, it is common to use units of measure corresponding to the weight of an object. So now we're going to go through an example one, and this example doesn't use calculus, so I'm going through it straight away. But we want to determine the work done in lifting a 50-pound object 4 feet. So here you're starting with a 50-pound object, you lift it up 4 feet. How much work did you do? The work is equal to F times D, and the units on this are the force, in this case, is in pounds, because that's a unit of force, and the distance was feet, so these are called foot-pounds. So, and units are actually a big deal in your engineering courses, a lesser deal in this math course. But in the U.S. measurement system, work is expressed in foot-pounds or perhaps foot-tons. In the CGS system, that is centigram, gram, centimeter, gram, and second system, it's called a dyne, and a dyne is the force required to produce an acceleration of 1 centimeter per second squared on a mass of 1 gram. There are other units as well. MKS is meter kilogram second system, and so there we use things like Newton meters, and a Newton meter is called a joule. So units are a big deal, and just kind of go with the flow on this, but in your engineering courses these will be very significant issues, and you should pay attention to units. But now we move to more of a calculus thing, so let's talk about this. So what we're going to do is we're going to talk about a variable force, and that means that the force changes with respect to where you are. So instead of the force being constant, a variable force is applied, and we need calculus to do this. So we'll talk about a force required to compress a string increases as the spring is compressed further. So what we do is what we always do, we break things into little pieces. And so we're going along a straight line, and we're moving from x equal a to x equal b. So we bust this into a whole bunch of little pieces, and so we break it into little pieces where we go from a, which we'll call x0 here, to b, which we'll call xn, and delta xi is going to be the length of the ith interval. And in each each of these subintervals, we choose a value in there, and we just say, well, what's the force at that point? So you see the change in work then in the ith unit is, well, you're moving something that is very close to f at that c sub I point, and in fact if we say it's constant, it's f of c sub I, that is a constant number times delta x. But you see, you have to do this, all of this work, not just the work done in moving from I minus 1 to xi, And so we're going to add these things up. So we'll add up all the little pieces of work, and we'll get W is equal to the summation as I goes from 1 to n of delta W sub I. But we were calling each one of those little delta W sub i's F at C sub I delta X. And you can kind of see that this is starting to look like a Riemann sum. So this approximation becomes better as n goes to infinity, and also we do have to have that the longest subinterval, the length of that has to go to 0. So the work done is the Riemann sum. And we take the limit of the Riemann sums and we get the integral. So the work done for a variable force F is F of X integrated over d of X as X goes from A to B. And that's the definition of work. So if an object is moved along a straight line, and this is straight line motion, by a continuously varying force F of X, and that force is in the direction of the motion, then the work done, W, by the force on the object in moving from x equal A to x equal B is the integral from A to B of F of X dx. Now we will use some fundamental laws of physics. I'm teaching you all the physics you need to know. The first one you need to know is Hooke's law. The force F required to compress or stretch a spring within its elastic limits is proportional to the distance that the spring is compressed or stretched from its initial limit. So that here F is equal to K times D. But you want to realize that the D is a variable. K is a spring constant, and that depends on the stoutness of the spring. And I guess I said all of that. We also have Newton's law of universal gravitation. The force F of attraction between two particles of masses m1 and m2 is proportional to the product of the masses and inversely proportional to the square of the distances between the two particles. That is, F is equal to, this is a constant called the universal gravitational constant. This is the value for it in these units. You have to be concerned about units, but it's proportional to the product of the two masses divided by the distance. Here the variable is not the masses, but the variable is the distance between the centers of masses of the two masses. So this is an important law, and this is Newton's law of universal gravitation, and again D is the variable. We also have a similar law for electrical things. The force capital F between two charges Q1 and Q2 in a vacuum is proportional to the product of the charges and inversely proportional to the square of the distance between the two charges. Now notice that this thing looks a lot like this thing, except the constant is way different and the product of the two charges is there as well. And this is either a force of attraction if the charges are of different polarity sign. One might be a negative charge, the other might be a positive charge, or they're repulsive if the two charges bear the same sign. Okay, and there we go. So Hooke's law, Newton's law of universal gravitation, and Coulomb's law will happen in our work. So now here finally is a problem that is a calculus problem. A force of 750 pounds compresses a spring 3 inches from its natural length of 15 inches. Find the work done in compressing the spring an additional 3 inches. You know what to do. Let's see how you did. Okay, and here's a picture, and you're compressing it here, and then you're compressing it perhaps more here, and notice that the x is variable. Okay, by Hooke's law, f of x required to compress the spring x units from its natural length is kx, and k depends on the spring. So what we're going to do is we're going to use the data that we have, about 750 and 15 inches. We'll plug that in, so we say f of 3 is equal to 750 is k over 3, so that means k is 250, so that is the constant of proportionality for the spring we're dealing with, so f of x is equal to 250x, okay? And it's useful to think about what happens in a small segment of work. So if we had a force at a point x, that would be 250x, and if I change it just delta x, I get that. So that is kind of what this looks like. So in the limit, I'm going to be integrating from 3 to 6, 250x dx. I integrate this, I pull out the constant, add 1 to the exponent, divide by the new exponent, do the calculation, and I get this, and these are in inch pounds in this case. Now note that we did not integrate from 0 to 6 because you were asked to determine the work done in compressing the spring an additional 3 inches, not the first 3 inches. Let's do another problem. A space module weighing 15 metric tons on the surface of the Earth. How much work is done in propelling the module to a height of 800 miles above the Earth, as shown in a figure, and I'll show you the figure later. You should draw your own figure. We want to use 4,000 miles as the radius of the Earth, and we simplify this problem by not considering the effect of air resistance or the weight of the propellant. This actually is a pretty complicated problem if you consider all the factors. You know what to do. Let's see how you did. Now, it's important that you realize that we're going from the center of mass of the Earth, so that means this radius is involved, and that was 4,000 miles, and we're going 800 miles. So actually, we're talking about taking the rocket from 4,000 up to 4,800, okay? And let's see, because the weight of a body varies inversely as the square of its distance, the force F of x exerted by gravity is this. Now notice we're saying this is a constant because the gravitational constant is, we're taking that to be a constant, and the masses are the same because we're not talking about burning off the propellant, and so we have the mass of the rocket and the mass of the Earth, so that's just a big old constant. Now we can figure out what that constant is because the module weighs 15 metric tons, and so we're plugging 15 into there as the force, and c is whatever that constant is, but the distance is 4,000 miles. That's what it weighs on the surface of the Earth, and so we can solve for c, and we find c is this big number. So if we look at the little piece, then we're saying, well, when we look at just the delta work, it's the force times the distance increment, so it's going to be that big old constant over x squared, and that is delta x. So if we're going from 4,000, as I said, the surface of the Earth, to 4,800, we have this. So it's the integral from 4,000 to 4,800. There's my force function, that is dx. I integrate. Now notice that we pick up a minus sign when we integrate, but when we plug the numbers in, we get this, and so that is 10,000 mile tons, and if you changed that to foot pounds, it would be this big number. And you can also talk about what it would be in joules. But the concept is, how do we do the work problem? Now the solutions to those examples conform to our development. Notice each time we look at a little delta W, and after we look at delta W, then we are going to integrate that. And here we're talking about the increment here, but here we're talking about the distance. So we have those two kind of considerations. Let's look at the next example. And this is going to talk about a spherical tank of radius 8 feet is half full of oil, and the oil weighs 50 pounds per cubic foot. Find the work required to pump oil out through a hole in the top of the tank. You know what to do. Let's see how you did. Now, what you really want to do is draw a picture of this. So here's the picture that we're drawing of this, and we're drawing a little sliver here. And when we draw the sliver, we're going to say, well, how much work do I have to take to this? And an important thing is we're setting up a coordinate system here. And you get to pick your coordinate system, but the coordinate system that we're picking here is the one that's shown. Okay, so this is called y because we're moving in the y direction. This is called, this distance is called x, and we're taking the origin to be at the very base here. That's where 0, 0 is. Okay, So let's go through. We're considering the Oriole to be subdivided into little discs, and we'll look at each disc, and we'll talk about the work done to the disc, and then we'll integrate by adding up all the discs. So the increment of force in each disc is delta F is equal to the weight. Now that is 50 pounds per cubic foot times the volume. Now the volume is going to be the volume of this disc. So it is going to be delta Y is going to be this dimension, but this is going to be a circular disc. So that is going to be pi, and the radius of that is going to be x squared. So you see delta F is equal to 50 pi x squared delta Y pounds. Now it is important that you really think about this. And now we're going to talk about how far we have to move it. So as for a circle of radius 8, which is the full radius of the tank, and a center at 0, 8, you have x squared plus y minus 8 whole squared is equal to 8 squared, so x squared is equal to this. So you see what we're going to be able to do is we can write the force increment as 16y minus y squared, because that's what's happening with this slice. Make sure you understand that. And you see x is always going to be, x is going to always equal, x squared is always going to equal that at a height of y. Okay, so in the figure you see that a disk y from the bottom must be moved a total distance of, so we're here, that's the slice. This part is y, so I have to move it up to 16 minus y, so that is the distance. So the change in work is going to be delta F, which is all of this business, times how far we move it. It is 16 minus y. So this is 50 pi 16y minus y squared. This is delta y, and this is times 16 minus y. And you could simplify that a bit. So now what we're going to do is we're going to take this and we're going to integrate it from 0 to 8. And the reason we're doing that is because it's only half full, and we're taking it out the top. So we integrate this. Make sure you follow the integration. We do the calculation, and we get this as our answer. This is a very important example, and I will expect you to be able to do problems like this. So please make sure you understand this one. Here's another example. A 20-foot chain weighs 5 pounds per foot, is laid coiled on the ground like this, but you're picking it up like this with this scoop machine. How much work is required to raise one end of the chain to a height of 20 feet so it's fully extended like this, so it's just touching the ground? Now what you want to realize is each part of the chain is being moved a different distance. You know what to do. Let's see how you did. Okay. Well, we know that the chain is 5 pounds per foot and times the length. So the change, so taking a little sliver of this, delta F then is equal to 5 delta Y. And what we're going to be doing is, if we are at a height of Y, let's see, if we're yeah, so this is 5 delta Y times Y if you're lifting it Y. But some of it you're lifting 0 feet, and some of it you're lifting 20 feet. So the total amount of work is you're integrating from 0 to 20, 5y dy. We integrate this, plug in the numbers, and we get the answer. Again, I do expect you to be able to do problems like this, so make sure you understand this example. In our next example, we're going to consider a piston of radius r, and this involves thermodynamics, or a law in thermodynamics called Boyles Law. And what you really say is that if P represents the pressure of the gas in pounds per square foot against the piston head, and V represents the volume of the gas in cubic feet, the work increment involved in moving the piston, this is something that you find in internal combustion engines, delta feet, is delta W is equal to P times delta V. And here we're going to notice that if this is a circular cylinder, what's going to happen is that is the pressure of the gas times the area, because pressure is force per unit area. So force is pressure times area, and this is going to be pi r squared. And so that's going to be equal to P delta V. So the work as you expand from V0 to V1 is going to be P dV in the limit. And so, and we will have a pressure of the gas is inversely proportional to its volume. So you have the pressure is equal to K over V, and the K depends on what the gas is that you're using. So the integral becomes the work is equal to the integral from V0 to V1 of K V dV. So here we have another example. A quantity of gas with an initial volume of 1 cubic foot and a pressure of 500 pounds per square foot expands to a volume of 2 cubic feet. Find the work done by the gas. And again, we're using Boyles Law. Okay, let's see how you did. So P is equal to K over V, and we use our information to determine the gas constant for the gas that we're doing. So 500, V is 1, so K is equal to, plug it in here, 500 here, and 1 here, so K is 1. And so the work is going to be the integral from the initial velocity, not velocity, the initial volume to the final volume. And this is K over V dV. I plug in the 500 and I get a natural logarithm here, and this I would expect probably an exact answer, but if you're using a calculator you could get this as your answer in foot-pounds. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. God bless you all.